Hi everyone, Chris Tisdell here again. In this presentation, I'm going to continue my series of videos on mathematics, and I'm going to show you how to solve a differential equation. Now, this differential equation is called a second order differential equation, and it's linear, constant coefficients. The way we solve it is through a simple analysis of a quadratic equation, believe it or not. So let me share my screen with you, and we can get down to business. Now, let me just repeat that. We're solving a differential equation without any calculus, okay? All right. So here's the problem I'm going to step you through. This equation is an equation that features the derivatives of an unknown function y. Okay, so if y is, say, a function of x, then the dashes mean derivative with respect to x. All right. So what we're trying to do is find a function y that depends on x, whose second derivative plus 2 times its first derivative plus 17 times the function all cancels out to give 0. All right. Now, why would you want to look at a problem like this? Well, differential equations are amazing. They help us model and describe and better understand lots of dynamical phenomena around us. Okay, so they're fantastic equations to look at. Okay, so how do we get to the solution? How do we find this function that satisfies this? Well, one quick way is to use the following idea. We form a quadratic equation called the characteristic equation, which is just a quadratic. Okay, call that star. Okay, so what do we do? Well, you look at the number of the coefficients in front of each term in the left-hand side. So you've got a 1 there, a positive 2 there, and a positive 17 there. You take those numbers and you write down this corresponding equation for this problem. Okay, so the double prime goes to a squared, the single prime goes to a power 1, and the 0 prime goes to a power 0. Okay, so this kind of equation now is a quadratic equation, and there's no more differential equation. We've replaced the differential equation with an algebraic equation. Okay, so this quadratic equation is something that you would have seen it or do see at school, and you solve it just like you will solve a quadratic equation at school. You can use the quadratic formula, you can factorize, okay, or you can complete the square. Okay, so let me show you. Let's have a look and see what we can do for this one. All right, I could use the quadratic formula there, but I'm going to choose a faster, possibly faster, but an alternative method. Okay, I'm going to use an idea called completing the square. All right, so what I'm going to do is I'm going to take half this positive 2. I'm going to square it, and I'm going to add it and take it away. Okay, so we have the following. Okay, I'm just going to get rid of that 1 now. Okay, so I'm going to look at the coefficient of this lambda. It's positive 2. I'm going to take half of that, which is 1, and I'm going to square it, and I'm going to add it. Okay, now, so I don't change the equation, I need to take the same thing away. All right, now you'll notice that this is a perfect square. Okay, and this, when I simplify this, 17 minus 1, that's going to be a square as well. So I'm going to have a square there plus a square there. So I've written the left-hand side as what's known as the sum of squares. Okay, so let me show you what I mean. So the left-hand side is this, plus, this is going to be 16, which is 4 squared. Okay? All right, so what I can do now is rearrange this bottom line. I can take the 16 to the other side and then take the square roots of both sides. Okay? Now, I'm going to have to take the square roots here, but I've got a negative. So what do? Well, there's an idea from complex numbers called I. It's the imaginary unit, and it satisfies the following condition. I squared equals -1. So let's write that -16 as 4i. Oh, sorry. It's 4i squared. Yeah, where I squared equals -1. Okay. All right. So let's take the square roots of both sides. On the left, on the right-hand side, I'm going to put in the plus/minus sign. Okay. So square root of both sides. It's going to be plus or minus the square root of that. Well, I'm going to the square's going to cancel, and I'm going to be left with 4i. So lambda equals, take the one to the other side, this. Okay. All right. Okay, so we've solved this characteristic equation. It took us a few lines. We've come up with complex values for our lambdas. Now, in this case, when we have complex values, this tells us that the solution to the original differential equation is of a special form. So let me share that with you. Okay, so we flag that the roots to our quadratic equation are complex. Okay, and so let me take a new page. The solution to star, our original problem, is of the following form. All right, so you can think of this being alpha plus or minus beta I. So alpha would be -1 in this case, beta would be +4. All right, so when we have complex roots with alpha and beta here, the general solution to our problem is the following. It's a linear combo of cosine beta x and sine beta x, and you've got this e to the alpha x out the front. A and b are just arbitrary constants. We don't know what they are, but they're just constants. Okay, so in this case, the alpha would be -1. So e to the alpha x will be e to the -x, and the beta would be +4. Okay. Okay, and so we have our solution. Okay, so let's just recap what we've done. We looked at the differential equation. We wrote down a corresponding characteristic equation. We solved it. It took us a little while, and we got complex roots. Now, when you have complex roots, the solution to your differential equation is of this form. I should write down a and b are constants here. Okay, and we're all done. Now, you can verify that this really is a solution by differentiating it once, twice, putting those things into the left-hand side. They should give you 0. Now, what happens if the roots to your characteristic equation aren't complex? Well, we've talked about that in other videos. We looked at the case where the roots were, say, real, this one here. The roots were real and unequal. You get a linear combo of exponentials. We also looked at the case where, say here, where the roots were real and equal. You get exponentials, but with an extra x in here. And this is like the third case, where you have complex roots. Okay. So why does the method work? How can you solve differential equations that you find in a calculus course by using quadratic equations? Well, I'm not going to explain that fully. I do have that in some other videos, but let me just give you a basic idea. You can break this down to a system of first order problems, and you solve each, you solve one and then the other. Okay, and that's where this solution comes out of. All right, so it is based on firm ground. Okay, but this method is very fast, and it's it's just fantastic. All right, I hope you enjoyed this presentation. Hope if you have any comments or any questions, you can always send me a message or post a comment. If you have any suggestions for other videos, I'd always love to hear them. So thanks for watching, everyone. See you soon. Bye.